Okay, we're going to talk about entropy, okay? First, we're going to talk about entropy on the macroscopic level, okay? The level we can kind of see. On the macroscopic level, it's related to the amount of energy that is unavailable to do work, okay? So what happens is we have a machine, and the machine is a cyclic process. So the machine does what it's going to do, and some of the work goes into doing work for the machine, but some of the energy is removed so that the machine can go back to its initial conditions, okay? And that energy that's removed doesn't go into doing work, and so therefore there is some that's unavailable to do work, okay? Entropy at the microscopic level is a little bit different, and sometimes you may have heard from chemistry class as it relating to a filing cabinet, okay? If we stick all our papers in a filing cabinet and file them away, they're nice and organized, okay? If we just pile them up, then they're not very organized. And this is a kind of an example, an analogy, okay? But when we're talking about it, what we're really saying is that at the microscopic level, the entropy is a measure of the number of ways that a system can be arranged, okay? So let's go ahead and look at an ice cube, okay? When you have a solid like an ice cube, okay, there's only so many ways that the particles can be arranged, okay, because it's a crystalline structure. Then you start to melt that ice cube, okay, and it becomes water, and they can kind of move around a little bit. Keep heating it up, and it becomes steam, and now those particles can move all over the place and kind of arrange themselves in a lot of different ways, okay? So when we talk about entropy at the microscopic level, we're saying it's a measure of the number of ways that a system can be arranged. And when we look at things, solids, pretty organized in their structure, okay? But when you heat things up and they become a gas, much less organized, okay? So there's more entropy with hotter substances than with cooler ones. Okay, so how does the second law of thermodynamics relate to entropy? Well, it says the total entropy of a closed system will either stay the same or increase. It's never going to decrease. So let's look at an example over here. We've got a cup of water. We stick an ice cube in it, okay? Well, we know that heat is going to flow from the water into the ice cube from hot to cold. Okay. Now, one thing that's going to happen is as this heat flows out of the water, the temperature of the water is going to decrease. Okay. When the temperature of the water decreases, okay, the entropy is going to decrease. So you might think, well, the entropy just decreased. It says that it has to stay the same or increase. Well, we're talking about the entire system here. Okay. And while the water was cooling, the ice cube was melting. Okay, so the entropy of the water went down because it cooled down, but the entropy of the ice cube is going up because it is melting, okay? So what we're saying here is that either the amount of entropy that the water went down by is equal to the amount the ice cube went up by, or the ice cube went up by more, and that's what the second law of thermodynamics says. And then we've got this heat death of the universe. Okay, that says that eventually all energy will be unavailable for work. At this point, all thermodynamic processes will cease. Okay, so at some point, this entropy is just always going to continue to either increase or stay the same. So in the spots where it's increasing, okay, it's going to keep increasing and increasing and increasing. Entropy is going to keep going on and going on. At some point, we're all going to be in thermal equilibrium. Okay, and heat always flows from hot to cold. Well, if we're all in thermal equilibrium, there's no heat flow. If there's no heat flow, machines can't do work, our bodies can't do work, and things will just cease to be able to happen.